built different.
Alright, let's do a bit of fact checking to see if he's actually built different or if the average human could do the same. There's two parts we need to measure. First, he falls for 23 frames and then his body absorbs the impact in 7 frames. So how long was he falling for? Well, 23 frames times 1 second per 30 frames gives us 0.77 seconds of falling. Likewise, if he absorbed the full impact in 7 frames, that's 0.23 seconds to stop. To calculate his final velocity before impact, we'll use a kinematic relationship. Acceleration is defined as the change in velocity over the change in time, which is 9.81 meters per second squared on Earth. Now we separate the variables and integrate. This is an indefinite integral, so we get velocity as a function of time is equal to 9.81 t plus c, and that c is the initial velocity, which is 0 in our case. Now let's plug in 0.77 seconds to figure out how fast he's going right before impact. This value comes out to 7.55 meters per second. So that's the final velocity right before impact, and since we're now moving on to the impact section, we're going to use kinetics to calculate the force on the body. Now is a good time to take note that it takes about 4,000 newtons to break the average person's femur, which is the strongest bone. That will be what we're comparing to. Anyway, now we'll use Newton's second law, again replacing acceleration with the time derivative of velocity. Just like we did before, multiply the dt to both sides, and we get f dt is equal to mdv, which we can now integrate. This will be a definite integral from 1 to 2, where 1's the starting point before impact and 2's after impact. Is the mass of Mr. Built different a function of velocity? Well, unless he's burning some crazy amount of calories on the way down, no, it's just a constant and we can take it out. Now we evaluate our definite integral and we can write it as m delta v. The left hand side of this equation isn't quite as obvious. Is the force a function of time? Let's use a force versus time graph as a tool to help us understand this question. So we're looking at the force with respect to time from 0 to 0.23 seconds when he finally stops. So we're asking, during this impact, was the force changing with time? If we had force transducers on him, would it be a large force at the beginning and less later? Or would it be the other way around? Since we don't know, the best thing to do is to assume that he somehow distributed the force evenly over time. And the total area under this curve represents the momentum change. We'll talk about that in a sec. Since the force here is the same here, the force is constant and we can take it out of the integral just like we did on the right hand side. What we're left with is the force times the change in time. Now we can solve for force, but this force is actually the average force, which happens to be the maximum in our example. The dude in the video is pretty short, no offense, so I'm going to guess around 60 kilograms. I could be off though. So 60 kilograms times 7.55 meters per second divided by our stopping time, 0.23 seconds, and then the units check out. So if he's able to distribute the impact evenly with time, his body only experiences about 2,000 newtons of force, which is much less than the 4,000 needed to snap an average person's leg. But I can't stress the importance of this evenly distributed weight enough. Let's extend this graph for another circumstance where this guy idiotically straight legs it. Immediately upon impact, he's got a much higher force than he does later, and while the area under this curve, representing the momentum exchange, is still the same, the peak amount of force he experienced might be well above 4,000 newtons, and at that point his legs certainly would look different. So to conclude, I wouldn't say he's built different, but I would say he uses some good technique.